So we started talking about derivatives. We discussed the limitations of symbolic differentiation. It has its place, but is not used super heavily in optimization. And then we discussed this idea of finite differencing. Finite differencing was pretty powerful in the sense that we didn't have to know anything about the function, right? It's just a black box. All we have to do is be able to give it an x, get back an f, and we can evaluate derivatives. That's really useful, but it has some limitations. One that we saw is that it's going to take nx function evaluation. So if I have 30 design variables, at a minimum, I'm going to have to evaluate my function and then my function 30 other times, at these nearby points in each dimension, just to get one gradient. And I have to do that at every iteration. So this can become expensive. The other problem is we saw is that subtractive cancellation limits our accuracy. And so we at best get about half of our digits in precision. So, maybe 8 digits precision. In practice, usually more like 6. And so it has those two sort of big limitations. We're going to talk about a new method today called complex step. I'm going to first just illustrate with an example. So let me share my terminal here. Just going to open up programming language here. Remember, we've been looking at this function last time that was, let's see, it was something like this, the square root of sine of x cubed plus the cosine of x cubed, just some example function. Yeah. Okay, and at f equals 2, so let's say x equals 2, we could derive an exact derivative for any point, right? Because we could do this symbolically. It's not too hard. But at x equals 2, the exact derivative is this, just for reference. And remember last time we found that a good step size, maybe around either -6, either -7 or so for this problem. And so if I did f of x plus h minus f of x, oops, and I divide that by h, that gives me an estimate for my derivative. And so let's call this finite. So if I take that minus my exact, you can see it's pretty good. It's not great, but I got about, I don't know, 6 digits, maybe 7 digits of accuracy. But if I want really small, let's do something really small, because ideally, right, I want to make this really small to eliminate the truncation error from my Taylor series. So if I go smaller, I'm going to get 0, right? It's just useless. Okay, so we're going to try something different. We're going to take an imaginary step using complex numbers. So sounds really weird, right? So in MATLAB, we use I for an imaginary number. In Python, J, and Julia, we use IM for imaginary. So I'm going to take an imaginary step. I'm going to say h times some imaginary number, okay? And I'm going to just take the imaginary part of this, divide by h. Okay, I'll explain why, but let's just go with this for now. We're going to do this really weird thing. My original function isn't a complex function, right? And I don't want complex numbers. I want a real derivative. It's a real function with real derivatives, but I'm just going to give it this imaginary number, take the imaginary part of the thing that comes out, divide by h, and I get this. If we compare it to df, you can see it agrees all the way, 15, basically exact, machine precision, right? The last number varies, but that will always kind of generally vary. So machine precision, an exact estimate here, effectively. So let's call this df complex. If I subtract those two, I'm basically getting the machine precision almost. All right. Okay, so what's going on? I did this really weird thing, got an exact derivative. Notice I still didn't have to know anything about what's going on inside the function. All I have to do is be able to call the function. Well, I guess I have to be able to call the function with complex numbers, but I didn't have to change anything for that to happen here in this case. I just passed in this complex number, took the imaginary part of it, got my exact derivative. Seems pretty awesome. It is pretty cool. Okay, so let's see. I'm gonna go back and share my other screen if I can figure out how to do that. There we go. All right, almost there. There we go. Okay, so this is called the complex step method, and let's try to derive it, or at least one way to derive it. We'll do this again with the Taylor series, just like we did with forward differencing and central differencing. So I'm just going to do this in 1D first. It'll be easier. Let's say I got my function, and we have been doing a Taylor series where we do like a step, right? X plus h. Well, let's again do that imaginary step, I times h. I is my imaginary number here, right? And let's just do a Taylor series expansion. So I'm going to still get f of x, and then it's going to look exactly the same as everything before, but instead of an h coming out, I get an ih, right? Times my first derivative plus, now I'm going to get ih squared times my second derivative over 2, and so on. Okay, so notice this is going to be, let me write it out again, f of x plus I times h, f prime of x, I squared, right? Remember what I squared is just -1, so this becomes minus h squared over 2, f double prime of x, and then I get, if I was to keep going, the next term would give me an I cubed, so 2 of those would turn into a -1. So I guess I'd still have a negative sign here. I'd have a minus I h cubed over 3 factorial times f triple prime of x, and so on. Okay, and remember, the thing I want is the derivative. I'm trying to solve for f prime of x. So I'd like you to just take a second, see if you could do that. See if you could solve it, pause, and try to solve for that. Okay, so like before, we're going to truncate the series, but we're not going to do that yet. Let's first notice the thing that we want is f prime of x, but it's got this I in front of it, and I don't really want I, right? That's just some weird thing that's there because I took this imaginary step. So what I'm going to do is I'm going to take the imaginary part of both sides. Right, so the imaginary part, right, this is going to be, because remember, I could write this whole thing, I could lump it into something like a plus bi, right? Where this would be the real part, this is the imaginary part. So for example, this term would contribute to the real part, this would contribute to the real part. These ones with i's in front of them, we'd all group here into this b term, right? So I just want this one, the imaginary part, because I want to pull this term out. So let's do that. I don't know, f is just some generic thing, so I'm just going to have to write it this way, the imaginary part of f of x plus ih. I don't know what that is. But on this right-hand side, right, this goes away because that's real. This is real, that goes away. So I'm just going to pull out this and this, right? That's that b part of a plus bi. So I have h times f prime of x minus h cubed over 3 factorial f triple prime of x. All right, so now I'm going to truncate the series. So we're going to get rid of, and of course there's other terms. Right now it's going to have the first derivative, the third derivative, the fifth, and so on, all the odd powers. So I have f prime of x plus, this is now second order because I didn't get rid of the second order term. It actually just disappeared because I took the imaginary part. I didn't have to truncate it. So this is still second order. And now I can solve for f prime of x. F prime of x equals the imaginary part of f of x plus ih divided by h. And that's exactly what I did in that little demo, right? I took this imaginary step, I added an imaginary step, took the imaginary part of that complex number, and then divided by h. And this Taylor series expansion says that should give me an estimate for my derivative. And we could do the same thing in multiple dimensions. So in ND, this was in n dimensions, we'd have the partial of f with respect to xj, for example. That would be the imaginary part of f, where we would add an imaginary step in just the jth direction only, right? We have to do this one at a time, just like finite difference, one at a time, divided by h. So basically the same kind of thing. All right, So this is crazy, but it works. And so what's the real benefit here? Well, there's one nice benefit here, right? It says, well, the order is h squared compared to forward difference, which was h, but that really doesn't matter too much. Um, what really matters here, notice what's different about this formula. Take a look compared to our, I mean, besides the fact there's complex numbers in here. Remember, for both forward difference, central difference, and now complex step, these are all Taylor series. We have some error term, and whether it's h or h squared, we want h to be as small as possible. This is our truncation error. So the whole key to get this derivative accurate is to make h really small, right? That eliminates truncation error. But what was the problem with the forward and the central difference? When we made h really small, what happened? Remember that we got subtractive cancellation. So I've made a mess of things here. So I'm going to write another color here. Remember, we had things like f of x plus h minus f of x divided by h. And it was this problem where we subtracted two numbers that were really close. Right? This is, say, forward difference. It gave us a problem. We were making h small, and we divided two numbers that were really close. Now contrast that to what we're doing here. Notice I'm not subtracting two numbers. I evaluate the function once, and I just take the imaginary part of that. I didn't have to subtract f of x. I didn't have to subtract two numbers. So I actually don't run into the subtractive cancellation error. That means we can make h basically as small as we want, avoiding underflow in the computer. So we can use something like what I did in the example, 1e to the minus 30. That's a very typical one. And basically, well, at that point, truncation error is well below machine precision. So we can get a numerically exact derivative or gradient derivatives or whatever we want um, from this method. So that's really cool. It still has its downsides, right? So for example, I have to evaluate this nx times. So if I had 30 design variables, I've got to evaluate my function 30 times. And the cost is more than forward finite difference. I'd say it's more comparable to central difference, because even though we evaluate this only once for each direction, we have to carry both the real and imaginary part. So it's effectively double the cost. So it's more like central difference. So this cost is pretty comparable to central difference. So we didn't really fix the problem of computational cost. It still can be expensive if my number of design variables are large. But we did address the issue of accuracy. I can now get my full machine precision, albeit by doing this really weird kind of thing. The other caveat is that I need to be able to evaluate complex numbers, and that usually, not always, but usually requires access to the source. So if I have this closed source binary, this often won't work. It can, it depends, but often we have to make some minor changes. So for example, in a compiled language like Fortran and C, we have to change all the reals to complex. In languages like MATLAB and Julia, you generally don't have to do anything. Most functions are already overloaded for complex. In Python, you may have to import C math instead of math, but most things will just work. There are a few other minor changes that you have to make. I'll mention those in a second, but for the most part, usually don't have to do much, and it will usually just work. But that's not necessarily guaranteed. Like I said, that's why I say we usually need to have access to the source. So here's a good sort of visual of the three methods that we've talked about. Well, we've talked about symbolic, but these three differencing methods that we've talked about. So here's some function. It's another 1D function. And we're comparing these three methods. And this is the error versus the exact derivative, right? And so 10 to the minus 16 would be our sort of machine precision here for these floating point numbers. And we're showing different step sizes as we've done. And I guess we kind of plotted this a little backwards, but the idea here was to show these bigger steps first and get smaller and smaller as we go to the right. So with forward difference, as we expect, right, we get smaller and smaller error as the step size becomes smaller. And if we didn't have subtractive cancellation, if we had that infinite number of digits, this would just keep going down in a straight line with this slope of 1 on a log-log plot, because that's a first order method. The truncation error was order h. Central difference, on the other hand, has a steeper slope of 2 because it's a second order method, right? It had the central difference, the Taylor series is truncated with the quadratic terms. So it's a little bit steeper. So we actually get a little bit more accuracy, a little more reduce the error a little bit. We usually get a couple more digits, 2 to 3 more digits. But again, we hit subtractive cancellation, and instead of going straight down at this -2 slope, we start losing digits, and both of them eventually, the error here is now 1, meaning 100%. The error is complete, right? We're predicting a derivative of 0, which is totally bogus, unless we were at the optimum, then we'd just be lucky, right? So again, if we had infinite digits, we keep going. So we're basically balancing truncation error, which wants to keep going this way, with subtractive cancellation, which means we can't go too far this way. So there's some sort of balance point. And as we talked about last time, there's some rules of thumb. It's a little bit different for each problem, but as a relative step size, usually say around 10 to the -6, 10 to the -7 for forward difference, maybe more like 10 to the -4 to 10 to the -5 for central difference. Those are just rules of thumb. It's about the square root of machine precision versus the cube root of machine precision. I shouldn't say machine precision, the precision of your function. Okay, but complex step, on the other hand, we still get that quadratic convergence, but that's not really the big deal. Big deal is that we can keep going. We don't get that subtractive cancellation, so we can get machine precision. We can just pick a number over here. In practice, people usually use like 10 to the -20 to 10 to the -40. I usually just use 10 to the -30. We don't have to really mess with choosing a step size, just kind of pick it beforehand, and it's going to work. We're going to get really accurate derivatives, just like that. So this is really cool. Okay, so let's just kind of recap. I think I said some of these things already, but I just want to, I don't know if I said all of them. So even though we're giving in imaginary numbers and we're getting out complex values and taking the imaginary part, we're using real functions. Real functions, right? I mean, real as in these are real numbers, and we're getting out real derivatives, right? With the complex numbers was just a means to the end. It didn't have anything to do with the fact that there were complex numbers in our analysis, or that we had to write it, or that our analysis somehow needs complex numbers. It was just a regular function, just with regular real numbers, floating point numbers that we used, and we want a derivative that's real, and that's how it works. Now, I should say, you can have a function, like let's say you have a function that actually uses complex numbers. That will work too. There's a little more work you have to do there, but this method can be used with just a little more effort. No subtractive cancellation. This is the big deal here. That means there's only truncation error that we have to deal with, and that we can basically eliminate. Or that we can eliminate to machine precision just by taking a really small step size. So we can get accurate derivatives to machine precision. Okay, so we addressed that weakness of finite differencing. What we didn't address, what's still a limitation, is the cost is still proportional to nx, and it's really similar, I'd say, to central differencing. Okay, and in practice, so I mentioned there's some things that we may need to do. So like I said, we generally need to have access to the source, in part because, like I said, we may, not always, like some languages it's just going to work. Other languages, we may have to change some of the reals to complex. But many of the times we don't have to do much of, not too much. So some things we do have to do, like if we have relational operators, like if we have if, else, less than, greater than, those we are generally, those are just control flow, right? We want to hit the same sections of the code that we would have otherwise. Putting in complex numbers, we don't want that to change. So what we want to do in that case is just compare the real parts, right? That also is going to affect max and min if we were using that, although generally we wouldn't necessarily use that in most inside the engineering optimization. That usually come out in the optimization rather than the analysis. But any of these comparison operators, we want to compare the real parts so that we follow the same control flow. So sometimes there's some changes to the source we need to make. And then Some functions we need to redefine or overload. One example is absolute value, because it's actually defined differently it's not complex analytic, but we can redefine one that will work pretty easily. Some trigonometric functions, again, depending on the language, the programming language, will have subtraction operations in them that won't work well with these really small step sizes, but these can all be addressed. And in fact, there are tools to do this. There's a link in the book if you're interested, but there were automated scripts for many languages that either we can just overload these automatically or we can run a script just to kind of add these functions. So it's often fairly automatic that if you just add this header file or you run the script, that you can complexify, if you will, your code so that it will just work. But like I said, in general, we do need usually access to the source. For a simple function like I showed, then you don't, in a language that's overloaded like MATLAB or Julia. But often we need to make some small changes. They're not too bad usually. Like I said, most of the time they can be automated, but they do exist. So it is a little more work than finite differences. It can't be just this automated thing. This is why there's not a default in, say, an optimization package, because finite difference we can always just do, assuming you provided a smooth function. A complex step we can't necessarily do. You have to put in maybe a little bit of effort at least. Okay, so that's it for today. It's a really cool method, but we're going to learn another method that's I think more useful, even better, more widely useful next time. So stay tuned for that.